So welcome to the next lecture on signals and systems, and we proceed from where we stopped in the previous lecture by looking at another approach to convolution. In the previous lecture we had concluded that if we wish to calculate convolution, two approaches could be: one, to do it analytically, that means to write down the expression for the two functions to be convolved by writing down the integral and by identifying various regions of t in which the integral needs to be evaluated so as to get different expressions as a function of t. We noticed that in different intervals on the time axis there could be different expressions as a function of t. In some part of the time axis the integral could be 0, in some parts of the time axis the integral could be an exponential, and so on. The other approach that we considered related to thinking about the operation of convolution as an interaction between an input and an impulse response. So suppose we identified the impulse response with a system whose behavior we can describe otherwise. For example, we identified that if an LSI system has the impulse response ut, the unit step, it is a running integrator. In that case, one might be able to arrive at the output or at the convolution of the two signals by reasoning out what the system would do to that particular input signal. Right? That was another approach that we could take. Now today we look at a third approach based on a graphical method. So to that objective we had sort of identified the relation between h lambda and h t minus lambda the last time. Let's recall the relationship. We said that for a function h of lambda, so you see here I am just using lambda to denote the independent variable in the signal, right? For the function h of lambda, the function h of t minus lambda could be obtained for a fixed t. Remember here we are evaluating this for every possible value of t. So when you consider h of t minus lambda, it is for a given value of t. And how did we obtain h of t minus lambda? We obtained in two steps. We said this is equal to h of t plus lambda with lambda replaced by minus lambda. In other words, there are two steps in this process. The first step is to shift backwards by t. And the second step is to mirror about the point lambda equal to 0. Mirror the resultant about lambda equal to 0. All right. Now let's take an example. Suppose h of lambda looks like this. Then shift back by t. So h of t plus lambda will appear this way. And h of t minus lambda here this way. So please note here, each point of significance goes to the corresponding negative point. So minus t goes to plus t, minus t plus 1 goes to t minus 1, and minus t plus 2 goes to t minus 2. Alright, and this is a function of lambda. Now you see, this is for every value of t. So for every value of t, you have a different function ht minus lambda here. Now in fact, one way to think of this is to think of the lambda as a pair of rails and the function as a train moving on the rails with the engine located at t. Right? So it's interesting. What you notice about the relation between the original function and the function that is h of lambda and the function h of t minus lambda, whatever is at 0 appears at t in h of t minus lambda. Whatever is beyond 0 appears correspondingly in the same order before t. When that happens, because when you shift backward by t and reflect, that process of reflection introduces reverse motion. So whatever is after 0 comes before t. This must be emphasized. And whatever is before 0 comes after t in the same order. So this is a neat and quick. Graphically, this is a quick way of writing down h of t minus lambda. Let's employ this approach to quickly writing down by inspection the function h of t minus lambda for another example. Okay? Suppose we had this h of lambda. To write down h of t minus lambda. How would it appear? By inspection I can straight away write it down. So I can write down the point 0 comes to point t. Whatever comes after comes before t. So here you have t minus 1 and t minus 2. And whatever comes before 0 comes after t. This is the situation. So here we have h of t minus lambda is a function of lambda. Of course, please interpret this as a straight line. It's a flat line. I mean, it's a deficiency in drawing. So that makes it clear to us how to construct h of t minus lambda from h of lambda, right? By inspection. Now, based on this, we'd like to construct an approach to convolution. So let's take a simple situation. Suppose you have one rectangular block and you wish to convolve this with another rectangular block. By a rectangular block, I mean a function that looks like this. So we wish to convolve this xt, a function that is 1 from 0 to a, right? This is xt and this is ht. I wish to convolve them. Now, you see, there is a choice before us. We can choose to fix, you see, the point is we wish to calculate this convolution. So, we wish to calculate x of lambda, h t minus lambda, t lambda. So, of course, we can take one approach here whereby we fix x, that means we write x of lambda looks like this. I mean, there is no change except that the variable t is now renamed lambda, that is all. And h of t minus lambda needs to be drawn this way. Is that right? Fine. Now, here, as I said, it is helpful to think of this as, you know, a pair of rails. So, think of lambda as a pair of rails on which this train moves. And think of this as a fixed train on the next pair of rails. So, you know, you have, the idea is that, you know, the calculation of convolution is the calculation of exchange between the two trains. That's the way of thinking about it, as a function of time. Now, visualize the situation. What are we trying to do in calculating the convolution? You need to calculate the convolution for every point in time. For every t, you have to calculate a value. How will you calculate the value? For that t, multiply these functions and find the area under the product. That's the convolution at that point in time. Now, it is very clear that if t is less than 0, the product of the two functions is 0. So, therefore, the integral is 0. Let us assume that b is greater than a. For the moment, let us assume that b is greater than a. Okay, so it's without loss of generality because you can interchange the roles of x and h anyway, right? So now what happens when t strikes? Now visualize this, you know, the engine is at t. Where will the convolution begin in such a situation where the engine just touches the last coach of the static train, right? That's when t becomes equal to 0 and the exchange begins from there, right? At t equal to 0, the convolution is, so let's start constructing it graphically, right? Now this is as a function of t, please remember. What we are doing here is to construct the output as a function of t. So at t equal to 0, of course the output is 0 because the product is 0. But as this train moves along the static train, the exchange continues up to what point in time? Well, you see, up to the point where there is some overlap between these two functions, right? Now, t, when let's look at the situation. As t moves from 0 to a, steadily you have a larger and larger rectangle in the product. You see, for t between 0 and a, what is the situation? The situation is that the interval between 0 to t has a product of 1 and everywhere else it is 0, right? I mean the overlap, so when t is between 0 and a, this part, the product x lambda into ht minus lambda is 1 for the interval 0 to t and 0 else. So what is the value of this? What is the area under that curve? T. So this grows as t a. So up to t equal to a, this grows as t. It grows as a straight line with a slope of 1. Now after that what happens? After that, visualize. So now the situation is, this is a longer train, that's a shorter train. The longer train has completely encompassed the shorter train. So the whole of the shorter train is exchanging itself with the longer train, right? And this would continue up to the point where the last bogie of this moving train strikes 0. That means the point t minus b strikes 0. Right? So up to the point t minus b equal to 0 or t equal to b, the area would continue to remain at the maximum, which is, yes, which is a into 1, that's a. So right from a up to b, let's write it down. Since b is greater than a, right from a up to b, the area continues to remain at 1. At a, I'm sorry, at a. And subsequently what happens? Subsequently, now the longer train begins to leave the platform, so to speak, or leave the shorter train, and a smaller and smaller part of them exchange. So now, which is the part which forms a non-zero product? The part from t minus b up to a. So now t minus b has gone beyond 0. So now you have only the area between t minus b and a coming into picture. So the product is 1 for the region t minus b to a. Right? So it's very clear that there also there's going to be a linear drop. There will be a linear drop in area up to the point where the last bogie finally touches the engine of this train. That's when t minus b is equal to a, or t is equal to a plus b. So from the point E up to the point a plus b, there is a linear drop. It goes to 0 at the point a plus b and then remains at 0, because after that there is no overlap anymore ever. So this is the convolution. This is x convolved with h. Alright, so this is x convolved with h. Now we notice that in this case, it is very convenient to reason out graphically. In fact, it will be extremely cumbersome to do the same thing analytically, because writing down these regions analytically can be very cumbersome and tricky. Whereas doing it graphically is very intuitively appealing and also much easier. Right? I'll give you another example. Suppose you have a function that looks like this. And you wish to convolve it with a function like this. I shan't calculate the whole convolution. What I'll do is simply to give you a feel of the regions. So this is the function. So we'll first, now here is an example where we have a choice. You see, convolution is commutative. So if you wish, you can call this the fixed train and this the moving train, or you can fix this function and move the other. Or if you prefer, you may fix this function and move the other. As you can see, it is normally more convenient to fix the function which is longer and move the function that is shorter. That is a most common guideline. It's not essential. One can do it the other way. But it is normally more convenient to fix the function that is longer, if there is one of the functions that is longer, and move the function that is shorter. So, if this is x of lambda, so to speak, then h of t minus lambda shall appear like this. And here again we can reason out in an exactly identical manner what will be the nature of the convolution. In fact, we can write it down. Yeah. So let this be 1, this point be half, right here. Now I shall calculate the convolution. So convolution of course is a function of t. Now again with the same reasoning, for t less than 0 there is no output. The output begins at t equal to 0. It rises as a straight line up to the point t equal to a and takes the value of a at t equal to a. Subsequently there is a tricky situation. You see, subsequently there is a tricky situation. You know, now afterwards there is, you know, you are losing some area and gaining some area here. Okay. In fact, you are losing double the area that you are gaining, so to speak. And where are you reaching finally? When you go to t equal to 2a, the area is coming down to half. When you reach t equal to 2a, this overlaps with this completely. So the area becomes a by 2. So it goes down from, at this point the area is a, it goes down to a by 2 at 2a here. I hope that's visible, yeah. So there is a straight line joining these two here. And afterwards, this continues to drop up to the point where t minus a becomes equal to 2a, which is t equal to 3a. So at 3a the area drops to 0 completely, right? So here we are at 3a, the area drops to 0 completely and then remains at 0 subsequently. This is the nature of the convolution. All right. Of course, you must, you know, these two lines have the same slope. Yeah. Now, there are some observations that we'd like to make from these two examples. The observation is, suppose one of the functions has a total extent of a units and the other function has a total extent of b units. What is the total extent of the convolution? A plus b, that's right. The total extent of the convolution is a plus b. In fact, we can go a step further. We can go a step further. We can show that if one of the functions begins at t1 and ends at t2, so x lambda begins at xt, so to speak, begins at t1 and ends at t2, whatever it might be, we don't care, just draw some arbitrary function. The other one begins at t3 and ends at t4, right? Yeah. Then x convolved with h begins at t1 plus t3 and ends at t2 plus t4. So whatever it is, right? Now I leave it to you as an exercise to show this. It's not at all difficult, it just involves finding the limits properly. So the beginning is the sum of these two beginnings, the end is the sum of those two ends. So this makes it very clear that the extent is the sum of these two extents. The extent t2 plus t4 minus t1 plus t3 is equal to t4 minus t2, t2 minus t1 plus t4 minus t3. So this is useful when you have functions that are compactly supported. We say a function is compactly supported if the interval on which it is non-zero is a finite part of the real axis. If there are two functions that are compactly supported, that is they are non-zero only over a finite range of the time axis, then the convolution is also compactly supported, and we can precisely find out the support. This is called the support of the function xt, and this is called the support of the function ht. The support of the function xt is from t1 to t2, the support of ht is from t3 to t4, and the support of the convolution can be obtained as t1 plus t2 up to t3 plus t4. Okay? Yes, okay. Yeah.
So shouldn't it depend on the relative values of t1, t2, t3 and t4, whether the convolution begins at t1 plus t3 and ends at t2 plus t4? If the moving train is xt and the fixed train is ht, then it should begin at t2 plus t3 and end at t1 plus t4. Shouldn't it be like that, sir?
Well, the question is whether this statement that the support of the convolution is t1 plus t3 up to t2 plus t4 depends on the values of t1, t2, t3 and t4. No, it doesn't. This is universal. So this can be shown independently of the values of, except for the fact, it is trivial that t2 is greater than or equal to t1 and t4 is greater than or equal to t3. Other than that, there is no other condition that I am assuming here. But beyond that, there is no other condition. It is always true that the convolution begins. In fact, you can prove this by looking at the limits of the convolution. Right? So establish the limits of the convolution. So I leave it to you as an exercise to prove this. If it cannot be done, we shall do it in a tutorial. Yeah? Yes, Uday. There is a question from Uday. Yeah?
So your first question, so the x of lambda goes to 0 after a, but the integral is not going to 0. So how do you explain that, sir?
Okay. Well, the question that Uday posed is that in our example, in our earlier example, in general, one of the functions goes to 0 after a certain value, say a, but the convolution has not gone to 0 after a. Then you must remember that there is a moving function, the other function is moving. So you must think of it as if it is dragging some of this area into a farther time. One must, the confusion is that it seems, at first glance it appears that when either of the functions is 0, you should not have a non-zero result. That's not true, because one of the functions is moving. So it might drag this non-zero into some other place on the time axis. Right? That's the way it's happening. Right?
When I calculate it analytically, I'll assume the function to be 0 beyond after that a. So I might get a different answer.
No. See, in the analytical expression, that's true. X of lambda when one of them. See, the point is where does the area overlap, right? So that is on the condition is on t, right? There's a joint condition. There's a joint condition between lambda and t. That's the catch. You see, that's the catch. There's a joint condition. If you wish to do it analytically, there's a joint condition between lambda. All right. What we'll do is, I think maybe since these questions have been raised, it might help to actually just work out the proof to this. It's not at all difficult. That will illustrate the point. So let x be let x be supported between t1 and t2, and let h be supported between t3 and t4. Then let us consider the integral yt. There's a question from Pune. Online. Is Pune connected? Pune is connected. Is it? Is Pune connected right now? Okay, yeah. There is a problem in giving the floor, so maybe Pune can send a text message and we'll answer it. Well, alright, while they send the text message, yes, so please let them send the text message, and moment it comes, please give me a signal, we'll just start this proof. So you see the convolution yt described by x lambda into ht minus lambda d lambda is going to have a, see now when is this convolution going to be non-zero? In the range where both of these are non-zero, which means lambda is between t1 and t2 and t minus lambda is between t4 and t3. Right? So the range where this is going to be non-zero is where both of these hold good. Right? Now it is very easy. See, now this is a joint condition on lambda and t. It's a joint condition on lambda and t. And we want the condition only on t. So we must eliminate lambda. And actually here it's extremely easy to do it. If we simply add the two inequalities, we shall get the condition on t. Right? So if you add them, you get t is between t1 plus t3. See, it is, you must remember when you are dealing with inequalities, to be very careful. You cannot do any possible operation on inequalities. Now addition is acceptable. Addition is acceptable. But it is not correct always to multiply inequalities, because you may be doing some, you might be introducing a negative number somewhere and so on. So anyway, addition is no problem. So t1 plus t3 less than equal to t less than equal to t2 plus t4. So that tells us the range of t in which this is non-zero. Okay. So t1 plus t3 less than equal to t less than equal to t2 plus t4 is the range of t in which you have a non-zero product. Alright. So have we got the question? Okay. Okay. But we can get the question from them, isn't it? Have they? Do they know that we have to send a text message? Okay. So, Pune, please send a text message, right? I hope you can hear us. Or otherwise, we are having a difficulty in transferring the floor. All right. So where were we? We were talking about the support of the convolution. Now you see, in general, there is no guideline on deciding which approach to convolution is better. I mean, there are situations where an analytical approach might be advantageous. There are situations where a graphical approach may be advantageous. One guideline which one can follow is that for compactly supported functions, particularly for functions that have a small support, and the function has a reasonably constant kind of pattern within the support. I mean, there are not too many variations in the nature of the function within the support. In such a situation, a graphical approach is desirable, right? An analytical approach might be desirable where the integral itself is easy to evaluate analytically as compared to graphical, right? So for example, if you have a function like this, see, sometimes one might want to make use of a combination of analytical and graphical approaches. So, in a situation where you have segments of straight lines, things like this, you may have a situation like this. A function, this is one of the functions, and this is the other function. Let's say it has another straight line segment like this. So if you wish to convolve these two functions, then a combination of an analytical and graphical approach might be desirable. What I mean by that is, it might be desirable to, look at the different regions and identify an expression for the different regions. All right. So here, for example, one can identify 3 or 4 distinct regions. In this situation, one can identify, suppose this point is A and this point is B on the time axis. So 0, A, B, and this is C. Then there are 4 distinct regions. So the first step is, of course, you can find out if this is the function, find out the shifted version of the function. So if this is x of lambda, and this is ht minus lambda, this is h of lambda, then we'll write down h of t minus lambda first. H of t minus lambda will have an appearance like this. It's going to right. So you agree with me, h of t minus lambda has an appearance like this. And what are the different regions? The different regions are when t is less than 0, so there is no overlap. The other region is when t is between 0 and a. The third region is when t is between a and b. And the fourth region is when t is beyond b. But there again there are 2 regions. There is a region in which t is beyond b. In fact, there is a region in which t is beyond b, but t minus c is between a and b. And then there is a region where t minus c is greater than b, so then the overlap is 0 again. So you see, one has to identify different regions. Now, in each region, the integral can be calculated analytically. Right? The integral can be calculated analytically. So that could be, one might need to make use of a combined graphical and analytical approach. In fact, that is probably the most expedient approach in most cases, the most useful approach in most cases. Right? Let me take an example of this graphical analytical approach together. Let's assume that you have to convolve 2 lines like this. So here we are, 2 sawtooths or 2 wedges, both of length 1, right? So both of these wedges are of length 1. So how do you describe these functions? Essentially these functions are, so x of lambda, this is, x of lambda, this is also h of lambda. So in fact x of lambda is equal to lambda for lambda between 0 and 1. That's the function that we are talking about. And same with h of lambda. So how does h of t minus lambda look? H of t minus lambda looks like this, an inverted wedge, t minus 1. And of course here the expression is going to be t minus lambda. Right? So if you look at the product, this is h of t minus lambda. If you look at the product, now which are the regions that we need to identify? So we'll identify three clear regions. So of course t less than 0, output 0. Convolution, x convolved with h is 0. Right? For t between, now the next region is for t between 0 and 1. So what is the situation there? In fact, we can erase this now. So for t between 0 and 1, the situation is that we are multiplying lambda by t minus lambda. So you have lambda into t minus lambda integrated over what range? Now you have to be careful. You see this, wherever t is, the integral runs only from 0 to t. So the integral is from 0 to t. Okay? And finally, when it starts leaving, so what's the situation? So when t reaches this point, now then of course it reaches its maximum value, and then it starts leaving. So when t is between 1 and 2, the integral runs from minus 1 to 1. But the expression is the same, lambda into t minus lambda. And finally, when t becomes greater than 2, then of course there is no overlap, and therefore the output is 0. When t becomes greater than 2, the output is 0. Right? So in general, one needs to use a combination of graphical and analytical approaches. In the graphical part of the approach normally helps us identify various regions. The analytical part of the approach helps us calculate the expression in each region. Right? So a combination of these two approaches is normally the best approach to take. So much so for methods of calculating convolution. Convolution is as much an art as a science. So to calculate convolutions efficiently is best done with practice. The more you convolve, the less convoluted the operation is. Right? So now we'll look at the consequences of some of the properties of convolution. Now we've already discussed one property of convolution, namely commutativity. Let us look at the consequence of commutativity in the context of systems. So it's all right. Commutativity has an interpretation. In the context of the operation itself, it says that if you convolve x with h, it's the same as convolving h with x. That is an operational statement. But does it also make a system statement? Okay? So in other words, suppose you have two systems placed in the following configuration. You have the input x of t fed to one system, S1, and the output of S1 fed to the next system, S2. And we look at the overall output here, let's call that yt. Now we wish to analyze the situation, right? And in the analysis that we want to make is in what way can we make a statement about the requirement of an ordering on these systems? Can we do that only with commutativity, or do we need something more about convolution? Let's see. So let both of these be LSI systems. So of course we assume both of them are linear shift invariant systems for the moment. And this one has an impulse response of H1, and this has an impulse response of H2. So the output here is X convolved with H1, emerging here. And the output Y is therefore X convolved with H1, the whole convolved with H2. Now, we naturally wish to ask, can this be regarded as x convolved with something. There are 2 points here. Can I replace this with x convolved with some? Can I replace it? That's the question first. Can I think of this as x convolved with something else? If so, what is that something else? There are 2 questions. We shall answer both those questions now. Right? So in fact, the most obvious choice is to see whether we can interchange the bracketing here. So, can we have x convolved with h1 equal, so true, can it be true that x convolved with h1 is equal to, x convolved with h1, the whole convolved with h2 is the same as x convolved with the whole of h1 convolved with h2. Is this true? In other words, does convolution obey the property of associativity? This is, as you recall, the property of associativity. So we first answer that question. Does convolution obey associativity? Well, it turns out that it does indeed. So let's write down. So we need to keep track of symbols, but otherwise the idea is not very complicated. So consider x convolved with h1. X convolved with h1 as a function of t is equal to x1 at lambda h1 t minus lambda d lambda. This you should interpret, you see, when we write something like this, we should interpret it as x convolved with h1 and the whole convolved with t. The whole at t, the whole at t. Right? So this is a function. This is a signal, x convolved with h1. Now x convolved with h1, the whole convolved with h2. The whole evaluated at t can be written as follows. We need to write this expression at a particular value of t. So what we'll do is, for the second convolution, we'll use a different variable of integration. Instead of using lambda, we'll use the variable phi for the second convolution. Right, so we'll write this as integral x1 at lambda h1 phi minus lambda. This part gives me this at phi. Okay, this part gives me this at phi. And now this again, this whole thing multiplied by h2 t minus phi d phi is the expression we are looking for. Okay, and here these two integrals, we must interpret this correctly. There are two integrals here. Here lambda runs from minus infinity to plus infinity, and here phi runs from minus infinity to plus infinity. That's the range of the integrals. Now, if I wish to first, see, what do I wish to do? I wish to compare this. I wish to compare this with the following. X convolved with the whole of h1 convolved with h2 evaluated at t. I wish to compare these two expressions. But it is sufficient for us to compare it with h1 convolved with h2 here convolved with x, because we know that convolution is commutative. Of course, I shouldn't do that. I shouldn't do that, because a function and an operation can be associative without being commutative. To take an example, matrix multiplication is associative without being commutative. So we shouldn't really do that. Let's not do it that way. It will be better to write down an expression for this independent of commutativity, right? Now that's essentially going to be the following. Let's write it down. So let's write it down. So let's keep this expression as it is. It's a little tricky. We'll write down this. We should not treat H1 convolve with H2 as one unit, right? So we have x at lambda. Let's write x at lambda. Doesn't matter. H1 convolve with H2 evaluated at t minus lambda. The whole evaluated at t minus lambda, d lambda. This is the expression that we are looking for. And of course, here lambda runs from minus infinity to plus infinity. So this is one part of the expression and this is the other. So we want to compare these here. Now I can rewrite this. Now you see H1 convolve with H2 evaluated at t minus lambda. So we can rewrite this. In brackets, this would be another integral. Now this time what we will do is, since we have already used lambda, we shall use another variable to denote the variable of integration for that convolution. Let's call that variable gamma, right? So we have H1 at gamma, H2 at t minus lambda minus gamma d gamma, and the whole d lambda. And this has gamma running from minus infinity to plus infinity. Is it all right? Yes. Now what is our interest? Our interest is in comparing this expression and this expression. And what is the difference that you notice between the two expressions? The difference is that gamma has been replaced by phi minus lambda, or rather vice versa. Phi minus lambda has been replaced by gamma. Now remember, phi and lambda are both variables of integration. So the idea is you are making the transformation of this double integral. You are making the transformation of this double integral on lambda and phi, both running from minus infinity to plus infinity, to a double integral on lambda and gamma, again lambda and gamma both running from minus to plus infinity. Now I leave it to you to make this transformation of variable. It's not very complicated. So I leave it to you. I don't need to work it out. I'm sure all of us can make transformations of variables. Substitute phi minus lambda equal to gamma, and therefore now you have two different variables of integration, gamma and lambda. Find out the limits. So if you make that substitution here and find out the limits on lambda and gamma, of course the limits on lambda remain the same. It's the limits of gamma that you need to work out. And in fact, it's not difficult to work out the limits on gamma. That's because if you look at it, phi runs independently from minus infinity to plus infinity, and lambda also runs independently from minus infinity to plus infinity. So difference will also run independently from minus infinity to plus infinity. So here the d lambda d phi element of integration can be shown equal to the d lambda d gamma element of integration. In fact, to be very precise, you should evaluate a Jacobian. The Jacobian would come out to be 1 here. So the element of integration d lambda d phi is equivalent to the element of integration d lambda d gamma, because the Jacobian is 1. Right? And with that, you can clearly see that if phi minus lambda is gamma, then t minus phi will become t minus lambda minus gamma. Right? So that would complete the argument. Right? So of course if phi minus lambda is gamma, then phi is lambda plus gamma, therefore T minus phi is T minus lambda minus gamma as you want, and that completes the equivalence of the two. Alright, so it's not a very difficult exercise to show that this is equal to this by using two-dimensional integration or integration with two variables, right, and by writing down the limits properly. Yeah. Anyway, that's a very important conclusion. It's a very important conclusion indeed. It tells us that convolution is associative. It tells us that convolution is associative. So, x convolved with h1 convolved with h2 is equivalent to x convolved with h1 convolved with h2. What is the physical meaning of this in the context of the two systems? It says that this is the overall output of the two systems, right? What is this? This is the output of another LSI system whose impulse response is h1 convolved with h2. So what does it say? It says that when you cascade two LSI systems, the cascade is equivalent to one LSI system whose impulse response is the convolution of those two systems. A short way of saying that is when you cascade two LSI systems, their impulse responses get multiplied. Their impulse responses get convolved. The impulse responses get convolved. Right? So now you see that statement is troublesome in the sense you must remember saying when you cascade two LSI systems, their impulse responses get convolved implicitly assumes that the result is an LSI system. Now that actually follows from this and needs to be emphasized. Two things follow from this. First, that when you cascade two LSI systems, the result is also an LSI system. Second, that the impulse response of the LSI system is the convolution of the impulse responses of the individual LSI systems. Now we come to the question, does it matter in what order you cascade? No, because h1 convolved with h2 is equal to h2 convolved with h1. So if you interchange the order of the LSI systems in the cascade, it leaves the overall result unaffected. Please note, this is true only for LSI systems, not for systems which are only L or only SI. It shall be possible to show counter examples of the other. Alright? With this then we conclude today's lecture and proceed the next time, right, on Monday.